welcome to the new lecture of the course, Properties of Materials. So, let us just briefly see the contents of last lecture, just brief recap. So, in the last lecture we talked about the basically slip in single crystals. So, we considered the geometry like this. So, you have a crystal which is subjected to a uniaxial stress, and let us say we have a slip plane which is oriented in this fashion. Now, this slip plane, as we discussed, is a closed packed plane, or it's a slip plane belonging to slip system. So, as a result it will have a slip direction. Let us say this is the slip direction and this is the slip plane, and so this tensile axis makes angle phi 1 and phi 2 with respect to the tensile axis. So, these so let us say phi 1 is the angle between, sorry, phi 1 is this and this is phi 2. Okay. So, it makes angle between, so the angle between the tensile axis and the plane normal is phi 1, and the angle between the slip direction and the tensile axis is the phi 2. So, based on this we resolved what we call as shear stress tau RSS, which is sigma into cos phi 1 into cos phi 2, and this product of cos phi 1 and cos phi 2 is called as Schmidt factor, and sigma is nothing but force divided by area. Okay. Now, this resolved shear stress has to exceed a critical stress which is called as tau CRSS, critical resolved shear stress, which is sigma y into cos phi 1 into cos phi 2. So, CRSS is a material characteristic characteristics. So, sigma y changes with the orientation. So, the product of sigma y and the orientation dependent parameters, that are phi 1 and phi 2, these two determine a value called as CRSS. So, the slip will start when tau RSS on a given plane will exceed tau CRSS. So, essentially what you are saying is that if you plot tau RSS as a function of stress, then your slip will begin. Let us say at this point, this is the corresponding yield stress, and this will be the tau CRSS for that given configuration, and when tau RSS exceeds this value of tau CRSS, then only the slip will start. So, this is sigma basically, okay, and the slope of this will be cos phi 1 cos phi 2. So, essentially what we are saying is that tau CRSS is a material property or a material constant, whereas tau RSS and sigma y are dependent upon the orientation. So, these are, you can say, orientation dependent. So, if you have two plots, let us say one is this, another one is this. So, depending upon what you have here, this system corresponding to tau CRSS, this system will show. So, in this case, for the same value you have higher RSS, so this system will start yielding first. So, you have 1, you have 2. So, 1 will show yielding before the 2 because of higher resolved shear stress. So, basically the slip system with highest Schmidt factor, you can say slip system with highest Schmidt factor will be the active slip system. Okay. And so, they will basically, what it means is that when the slip systems are oriented favorably, with respect to tensile axis, maximizing the Schmidt factor. So CRSS will be achieved even at lower yield stresses as compared to systems which are unfavorably oriented. So you may have very high yield stress, but if the Schmidt factor is low, then your critical resolved shear stress will remain low. So, basically you want to maximize the Schmidt factor to reach the CRSS early to initiate the yielding at lower yield stresses. So now this is what the summary of slip-in systems, slip-in crystals is. Let us take an example of this. Okay. Now the example is, let us say you have a crystal. Okay, let us take a little difficult problem. Okay. So this is a bicrystal, let us say crystal 1 and crystal 2, and this is subjected to a stress sigma in this direction. So this direction for the crystal 1 is 1 1 1 and the direction for crystal 2 is 1 1 2. Let us say this is, these are crystals of same material. So you can say two crystals of same material, all right. So let us say we have a yield stress, let us say 100 MPa, or stress, not the yield stress, but stress is, so basically we are saying F divided by is equal to 100 MPa. So essentially if this is the situation in which we are in right now. So for first grain the stress is parallel to 111 axis, and for the second grain or crystal the stress is parallel to 112 axis, and they are joined in such fashion so that they make a vertical rod. So basically now the question is which crystal will yield first, and what will be the slip system. Okay, this is the problem, assuming that cross sectional area A1 is equal to A2. So cross sectional area is similar. So let us see this problem. Let us say phi 1 is the, so we know what phi 1 and phi 2 are, and so phi 1 let us say is the angle between tensile axis. So cos of angle between tensile axis and plane normal, and phi 2r is cos of angle between basically tensile axis and slip direction, all right. And let us say the material is FCC structured, all right. So basically we have 12 systems for FCC. So FCC has 12 slip systems, and we need to figure out which of these slip systems will have highest resolved stress, and which of these, and then compare the two of them, which one will. So let us first take the case what will happen if it was only one crystal. Let us say we work out both 1 and 2 separately, and we see which one will have highest resolved shear stress for which slip system, and then compare the two. Okay. So let us do this. So let us write down the slip systems for FCC. Slip systems for FCC can be written as, let us say the first one is 111, bar 1 10, second one is 111, sorry, 111 and 10 bar 1, third one is 111, 0 bar 1 1, fourth one is bar 111, 110, bar 111, 101 and bar 111, 01 bar 1. Okay. And then we have another direction, and making sure that, and these slip systems you can see, you can take the dot product will be equal to 0. Then we have third one third group of planes and directions, that is 1 bar 1 1 1 1 0, then we have 1 bar 1 1 1 0 bar 1, then we have 1 bar 1 1 0 1 1, then we have 1 1 bar 1, and the three corresponding directions will be 1 bar 1 0 1 0 1 and 0 1 1. So, these are slip systems. Let us say what is cos phi 1. So, crystal 1 tensile axis is 1 1 1. Okay. So, let us work out what is cos phi 1, cos phi 2. So, we can say that cos phi between two directions will be u1 u2 plus v1 v2 plus w1 w2 divided by square root of u1 square plus u2 square plus u3 square into u1 v1 and w1 square. Let me just make this change here. And u2 square plus v2 square plus w2 square. So, this is the angle between, you can say u1 v1 w1 and u2 v2 w2 in a cubic system. Okay. So, if that is the case, for the first one it will be 1, this will be 0, this will be 1, this will be 0, this will be 1, this will be 0. So, you can see that 1 and 1 1 are collinear. So, this is basically 3 divided by 3. So, this will be so this is basically, you can say for 1 1 1 the slip plane normal will also be 1 1 1. So, essentially you are calculating between the angle between 1 1 1 and 1 1 1, which is 1 1 1, basically 1 1 and 1. So, basically it is nothing but 3 divided by 3. So, this is same, and between these it will become 0, the dot product becomes 0. So, this is 1, this is 0 0 0. So, essentially the product of these cos phi 1 cos phi 2 will be equal to 0 0 0. So, essentially these slip systems will not be active. Okay. Now, let us work out for others. So, if you do the maths, first one will be 1 by 3, 1 by 3, 1 by 3. This will be 2 divided by root 6, 2 divided by root 6 and 0. So, the product will be 2 divided by 3 root 6, 2 divided by 3 root 6 and 0. Now, let us work out the third group of planes. So, 1 by 3, 1 by 3 and 1 by 3, if you take the dot product, and this will be 2 divided by root 6, 0 and 2 divided by root 6. So, if you take the cos of u1 u2 u1 u2 plus v1 v2 and so on and so forth, this will come to be 1 by 3 for all three of them. Here it will be 2 by root 6 for the first one, 0 for the second one, 2 by root 6 for the third one. So, this will be 2 divided by 3 root 6, 0 and 2 divided by 3 root 6. Now, work out for the fourth group of plane, that is 1 by 3, 1 by 3 and 1 by 3. This will be 0, 2 divided by root 6 and 2 divided by root 6. So, this will be 0, 2 divided by 3 root 6, 2 divided by 3 root 6. So, you can see that out of these 12 slip systems, for this orientation 1 1 1, 6 slip systems show 0 shear stress, which means they will not slip at all, whereas remaining 6 show similar value of stress. Alright. Now, let us see the crystal 2. So, basically you can see if it was crystal 1 alone, then either of these planes could have either of this slip system could have start slipping, because all of them have similar shear stresses or Schmidt factor. Now, let us look at the crystal 2. Crystal 2, again we calculate cos phi 1, cos phi 2 and cos phi 1, cos phi 2. So, here this will work out to be, now crystal 2 has orientation which is 1 1 2. So, if you take the 1 1 2 cos 1 1 2 versus 1 1 1 angle, then it will be 4 divided by square root of 6 into square root of 3 this will be 4 divided by square root of 6 into square root of 3, and this will again be 4 divided by square root of 6 into square root of 3. And for cos phi 2 this will be 0, this will be 1 divided by square root 2 into square root 6, and this will be 1 divided by square root 2 into square root 6. If you take the Schmidt factor, this will be 0, this will be 2 divided by 3 root 6, and this will be 2 divided by 3 root 6. Okay. So, you can do the maths again for this. This will be 2 divided by square root 3 into square root 6. This will be 2 divided by square root 3 into square root 6. This will be 2 divided by square root 3 into square root 6. This will become 2 divided by square root 2 into square root 6. This will be 3 divided by square root 2 square root 6, and this will be 1 divided by square root 2 into square root 6. So, if you now multiply, this will be 2 divided by 3 root 6, this will be 1 divided by square root 6, and this will be 1 divided by 3 root 6. Okay. So, this is how it will turn out to be. For the next one now, this is 2 divided by square root 3 into square root 6. This will be 2 divided by square root 2 into square root 6. This will become 2 divided by 3 root 6. For the next one, it is 2 divided by square root 3 into square root 6, and the other one will be 1 divided by square root 2 into square root 6, and the product becomes 1 divided by 3 root 6. This will be 2 divided by square root 3 6, 3 divided by square root 2 into square root 6, this becomes 1 divided by square root 6, and this will be 0, these two will be 0, these will be 0 as well. This will be 3 divided by square root 2 into square root 6 into 3 divided by square root 2 into square root 6. So, these 3 will show 0 Schmidt factor. So, we can see that here, first of all, if it was only crystal 1, then these could have slipped. Now, we have crystal 1 attached with crystal 6, we can see that the highest value is shown by this or this. So, basically crystal 2 shows higher shear stress than the crystal 1. So, crystal 2 will slip first on the slip systems which are basically bar 1 1 1 1 1 0, okay, and then it will be sorry, not this one, it would be the next one, bar 1 1 1 1 0 1. So, essentially we can say it is this slip system which shows higher shear stress, and then we have this slip system which shows higher shear stress. Okay. So, we can summarize from this, the answer will be crystal 2 will slip first on bar 1 1 1 and 1 0 1 and on 1 bar 1 1 0 1 1 systems, and that is because you can see, because these show higher value of because tau RSS will be equal to sigma into cos phi 1 cos phi 2. So, you can see that the stress will be equal to 100 MPa multiplied by 1 divided by root 6, 1 square root 6 MPa. So, this will be the value of resolved shear stress for this particular slip system. All other slip systems will show 0 stress. So, essentially what you are going to do, so the procedure basically is, for a given crystal, you need to first work out what tensile axis is, tensile axis direction, u v w, let us say u t w t, u t v t w t. Then you need to work out for all the slip systems, okay, for all the slip systems the phi 1 and phi 2 basically cos phi 1 and cos phi 2 for all the systems, slip systems. Compare cos phi 1 product of cos phi 2 and then determine the ones with highest tau RSS. So, let us say even if the value of tau RSS is this, if tau CRSS was let us say 100 MPa, then we can see that even with this orientation, tau RSS is lower than tau CRSS, slip will not occur. However, if tau RSS was more than tau CRSS, then slip will occur. So, which means you need to increase the value of sigma for that to happen. So, this is what we have done in what we have seen is basically a simple example of how one can calculate the resolved shear stress for a given orientation of crystal with respect to kind of slip systems that are present in the now what happens now we need to work out. So, this is the calculation of resolved shear stress. Okay. Now the question is, how do we calculate the theoretical shear strength of a material, and then we want to see are they in agreement with observed values. Okay. So, this is what we are going to do, and next, so let us see how do we do that. Let us say estimation of CRSS was first given by Frenkel in 1926. So, let us see what happens in a material. So, in a material you can see the atoms are placed in this fashion. They are placed in an ordered fashion in a lattice, and if you take the touching sphere model, then touching sphere model would be something like this. We have first row of atom. So, they are touching in the sense they actually do not touch because of electrostatic repulsion, but nevertheless for the sake of convenience let us consider that these are touching each other to the closest approximation. So, this is how you have a first row of atom, then you have second row of atom, and the spacing between them let us say is, so there is one spacing here. Okay. So, let us say this is B and this is A, and these are theoretical spacing, and basically what it means is that the potential energy of the crystal is minimum when the atoms are located at these positions. So, potential energy goes like this. So, at equilibrium positions 0 and 1, potential energy is minimum. So, let us say this is the position 0, 1, 2, 3, 4, 5. So, this is the 0 position. So, 0 position, 1 position, 2 position, potential energy is minimum, but when it comes to this position, let us say, so this atom when it moves to this position, then it comes on top of the next atom, and that is where the potential energy is maximum. So, let us say this is 0 prime. Okay. So, this is 0 prime, this is 0, this is 1. So, when the green atom let us say moves here, then the potential energy is, so this is the case of sort of a close packed. So, you can see the shear stress of a material also varies in this sinusoidal fashion. So, the shear stress varies. If you plot the shear stress, the shear stress varies in this fashion, which is a sinusoidal variation. The maximum amplitude that we want to apply is tau. We can apply is tau CRSS, and let us say this is the overall. So, this is where we have the change of slope. So, this is where your potential energy is maximum. So, this is your B, this is 0, and this distance will be B by 2. So, if you look at this distance, this will be basically, you can say this is, if this is B 0, this is B, this will be 0 B by 2. So, this is what, so this point corresponds to minima, this point also corresponds to minima, and this point corresponds to maxima in potential energy. So, what we want to do is that we want to now develop a framework of from this variation of shear stress and from this sort of schematic diagram of how atoms are placed in a solid considering touching sphere model, we want to develop a sort of simple mathematical framework of calculating resolved shear stress, and we will do that in the next lecture because we are running out of time now. So, what we have done in this lecture is basically we have looked at how do you work out the resolved shear stress for given orientation of crystal and the type of crystal in terms of material. So, if it is FCC for all the 12 slip systems, you work out the phi 1 and phi 2 values, and then you work out the product of cos phi 1 cos phi 2 and see on which of the systems the shear stress is the Schmidt factor is maximum, which will basically maximize the shear stress. But even then the resolved shear stress has to exceed the critical resolved shear stress, otherwise the yielding will not occur. So, we will continue our discussion of theoretical shear strength in the next lecture. Thank you.